Okay, class, we're at it again. Focusing on Exergy in a control volume for lesson 5. This is video 2 of 3 for this lesson. So we're going to talk directly about control volumes. The example that we used this past time was a turbine with flow or mass crossing control system coming in and out of this device across this control surface. Now I want to make sure that everyone remembers T0, P0 is that surrounding temperature and pressure, what we call the dead state. So you might imagine, say, 25 degrees Celsius and 1 atmosphere, or say 101 kPa, kilopascals, or 14.7 psi. Absolute pressure, not gauge pressure. So we're talking about what that means, basically all the surrounding conditions around the engine that it's operating inside of. Okay, so what we talked about last class, or last video rather, we closed that discussion with an equation describing flow exergy, right? And we had flow exergy on a specific basis was equal to this difference in enthalpies, a difference in specific entropy, a kinetic energy term, and a gravitational potential energy term, all on a specific basis. So these are, say, kilojoules per kilogram basis. And that was equation 12.43 that we saw. We could then describe it on a rate basis. So we had it on a rate basis, and that would be Exergy flow with a dot is equal to m dot Exergy flow, or specific flow exergy. So now let's talk about what this means for a control volume Exergy balance. So we're seeing up here in the top right hand corner, Exergy balance of control volume. So in this case, what we would see, so we have an Exergy balance of a control volume. And we could define this as being 0 is equal to the rate of exergy transfer as a result of heat transfer minus the rate of exergy exchange as a result of work plus that critical term that I have up there, which is our flow exergy. And this would be, say, the inlet. And we would then say minus our flow exergy. Let's see here. I drew that X a little different, so I'm going to erase it. Exiting. So to be clear, that nomenclature, those subscripts I and E in this context are inlet and exits. So if you have multiple inlets and exits, then you would need to account for those. For right now, we're just talking about single inlet, single exit devices. And then last, our rate of exergy destruction. So we would define these three here, or these four rather, as exergy transfers. Exergy transfers. And then this last one would be our exergy destroyed. Okay, so if we talk about each of these things, we would then say where our rate of exergy as a result of heat transfer would be defined as such. So remember, we could have multiple conditions or multiple locations in a system that are transferring heat into or out of the system. We have our dead state temperature, our boundary temperature, which you would often be, say, given in an exam or in a WPR, with our rate of heat transfer at any given condition J. So say you have an entire engine and you have heat transfer exiting heat exchanger, you also have heat transfer coming across a turbine if it's not adiabatic. So you could have multiple locations of that heat transfer. So this is, as we said earlier, this is the rate of Exergy transfer accompanying heat transfer. All right, so a form of energy transfer is now being used to describe what we have as Exergy, or a rate of Exergy transfer. So this, I meant to describe this. I want to call out something here, which is to say our heat transfer, definitely recall to win. Our convention for defining, what is positive and negative for heat transfer and work. On that note, let's talk about work. So we have our work, and we're going to say work IE in this case. Now, if you were focused just on this turbine, as you see on the right-hand side, this is work 1, 2. So that's defining just the rate of work that is being produced by that turbine. So if you were looking at the rate of Exergy transfer accompanying shaft power for this turbine, then you could just focus on that work 1, 2 if you were looking for the rate of Exergy transfer. So let's write that out. So this is, we have the rate of Exergy transfer accompanying shaft power. I think I'm going to run out of space here, so let's stack these on top of each other. Accompanying shaft power. Okay, and then last, a rate of Exergy destruction. So our dead state temperature, T0, times our rate of entropy production. So this is our rate of Exergy destruction due to the presence of irreversibilities. So recall from MC311 that irreversibilities could be things like, say, generation of heat, like, say, friction. So if you had a flow that was not inviscid, you're inevitably going to have shear stress and friction. You're going to generate heat. Those are going to be irreversibilities. You could also have heat transfer through a finite temperature difference. So rather than an infinitesimally small temperature difference, that's going to produce irreversibilities. We're going to then produce entropy, and thereby, by analogy, we're also going to destroy Exergy, which basically means that we're not going to get out as much work as we previously would have wanted to. So, jumping forward here, continuing that same discussion. So, this the idea of our Exergy basically balance, this is going to account. So it counts for the disposition of Exergy during a steady flow process. And I do need to emphasize that steady flow process, because everything we're talking about right now is for steady flow devices. Okay? We've got a few implications here. This whole board here is just following on or continuing the previous board, just to make sure you're tracking that. It's not a separate thought, it's a continuation of the previous thought. So the implications here are that processes, or a process that produces entropy, as I noted previously, sort of by analogy, that means it must destroy Exergy. And I do want to highlight something or note something. Remember, that exergy is usable energy. Right? So keep thinking about usable energy. So when we say destroy exergy, it basically means that the amount of usable energy is going to decrease. And as we said earlier, our exergy destruction is going to be directly proportional to the rate at which we are producing entropy. And that means that our exergy balance is in and of itself an alternate expression. An alternate expression for the second law of thermodynamics. I feel like every time we say one of the laws of thermodynamics, we should all stand up and announce them. It's a law of thermodynamics. So an implication there, right, is that exergy destruction, if we describe these in terms of, say, greater than equal to or less than equal to 0, if we said it's less than 0, equal to 0, or rather greater than 0 or equal to 0 or less than 0, then we would say this thing is irreversible. Right? It's irreversible because it's greater than 0. Exergy destruction is greater than 0, or by analogy that means we produced entropy. So it's an irreversible process. If it's equal to 0, it means we have a reversible process. It's an idealized case. And if it's less than 0, it is impossible. This is the type of thing where you as an engineer or thermodynamicist can then actually do analysis to figure out whether or not a proposed system is possible. It is a very powerful tool that can be in your toolkit. Okay, jumping forward here, let's talk about exergetic efficiency as compared to, say, just a typical or normal thermodynamic efficiency. This is a measure of how much exergy. So this is a measure of how much of exergy available basically is put to useful work. So available to, and this is a critical term, to an adiabatic device, right? Adiabatic, let me put a little underline under there. Device is converted to useful work, or in this case, let's be more specific with our statement, to useful exergy effect, basically just saying useful work. So the idea being here is that, say, a gallon of gasoline has a certain amount of exergy, or it has a certain amount of available work that it can do. Now you take that gallon of gasoline and you burn it, and it's going to produce a certain amount of heat, and that amount of heat can then do useful work, but in the process of burning gasoline you're going to create irreversibilities, and as a result of that you're going to have a non-idealized process, and subsequently you're not going to get everything out of it that you might have wanted to otherwise. So you're going to have some exergetic efficiency that is less than 1. Okay, so let's talk about some specific devices. You have a pump and, say, a compressor. And those exergetic efficiencies might be, excuse me, exergy, eta exergy of a pump and eta exergy of a compressor. And these respectively are going to be equations 12.54 and 12.55. So we would have exergy of a pump, or the efficiency. They're going to be the same equation. We have our potential to do work, or what we describe as our potential to do work using our flow exergy, divided by the rate of work that is required out of those systems in order to achieve the outcome that you wanted. So in the denominator, that is the actual amount of work required, and in the numerator, it is the idealized difference in exergy flow. So for a pump, it's going to need work into the system, work in negative. That's why we have that negative sign in the bottom, work in negative, right? Hip to win, work in negative. So the denominator actually becomes a positive term for a pump or a compressor. And in an idealized case, you have the exergy flow, which is in the numerator. And this whole thing can simplify to this statement of basically in the numerator is our exergy destruction divided by our work actual that's required for that pump or the compressor. Okay, let's talk about a turbine. So continuing a similar idea. So now our turbine exergetic efficiency. So in this case, eta EX of a turbine we'd say eta of that turbine. Now in the numerator, remember hip to win, we don't have that negative sign for a turbine because work out is positive. In the denominator, we have our difference in exergy flow. And now we have our statements of exergy destruction in the numerator, T naught times S production, or the rate of entropy production, which is equivalent to our exergy destruction. So recall this numerator is exergy destruction, or rate of it, just to help connect the dots there, right? And we are looking here at equation 12.53. So as a quick note regarding, say, a exergetic efficiency of a turbine. So exergetic efficiency of a turbine, if we do a little side comparison here, if we say the thermodynamic efficiency of a turbine, we would say H1 minus H2 divided by H1 minus H2S, if you recall from MC311. What you should realize in this conversation is that since the available work in the denominator of exergetic efficiency, available work is actually less than the ideal, like the total amount of energy that is in a flowing system. And as a result of that, the denominator for an exergetic efficiency is going to be larger. So for a turbine, we could then conclude, therefore, exergetic efficiency of a turbine is going to be greater than the standard thermodynamic efficiency of a turbine. Please wrap your mind around that idea. And then, shifting gears, let's identify one of the performance terms for a heat exchanger, exergetic efficiency. So exergetic efficiency of a heat exchanger. So we've got eta. Exergetic efficiency of this heat exchanger is then equal to our mass flow rates of the hot line and the cold line. In the numerator, it's the cold line. So Exergy flow of our cold line, so C2 minus exergetic flow C1 divided by our hot line H. And we have again a similar difference in our Exergy flow, except take note that the directionality of these, whether it's 2 minus 1, 1 minus 2, depends upon basically how the heat exchanger is set up. If you have cross-flow heat exchanger or if you have a counter-exchange heat exchanger, you will end up basically just make sure you recognize which one is the inlet and which one is the exit when I'm talking about these 1s and these 2s. So this statement here can then simplify further to be, again, in the numerator, description of our rate of Exergy destruction divided by our hot side Exergy flow H1 minus Exergy flow H2. Running out of space over there. Make sure, or I want to make sure that I clarify, right? C is our cold line on that heat exchanger, and H is our hot line on that heat exchanger. And this whole thing, to see the additional derivation and details, is equation 12.57. But please have that intuition as to, right, your heat exchanger or your exergetic efficiency is similar to your typical thermodynamic efficiency, except you're now dealing with a, for instance, like with the turbine, you're dealing with what is the available work, what is the available amount of energy for doing useful work, as opposed to what you saw in MC311, which was just the total amount of energy, or idealized total amount of energy, which in this case of the turbine was, say, described as H1, or enthalpy at state 1 minus the isentropic enthalpy at state 2, entering and exiting a turbine. So that gives you a crash course on control volume analysis using Exergy for an Exergy balance, as well as some of the performance metrics of using exergetic efficiency to define the performance of a steady state device. All of these, for now, we've been talking about adiabatic steady state devices. Okay, that wraps up video 2 of 3. The next video is going to give an example problem, so please walk through that closely to make sure that you understand, make sure basically that you complete all your practice work in running through practice problems. Okay, that's it.